In this video, we are going to go over some gas law practice problems. These can be a little confusing, so I want to give you a couple example problems of these types of questions. That way, when you do a CASA learning on this, it should be a little bit easier from the very start. So number one says, as the pressure on a given sample of gas increases at constant temperature, the mass of the sample does what? So a couple things. One, when we talk about the relationships of gases, we never mention mass. Okay, so the mass isn't going to change, right? But the other thing I want to mention is, see how they say at constant temperature, and I have it crossed out? Anytime something remains constant, that means it doesn't change. So you'll find out when we learn this formula, the formula that governs all of these rules, anytime something is constant, we basically ignore it. So if you see something's constant, you don't really have to worry about it too much. You just need to know, oh, it's constant, it's not changing. I can basically ignore that part of the equation or that part of the problem. So it's really just a question of pressure and mass. That's like saying, as the pressure on a rock were to increase. So if I take a rock and I squeeze it really hard, the mass of the sample, the weight of the rock, would it increase, decrease, or stay the same? It's not going to change no matter how hard I squeeze it. All right, and so that's one is really kind of like a trick question. Two, according to the kinetic theory of gases, that's the KMT, that's the theory of how gas molecules move, which assumption is correct? So this comes down to, do you have the KMT for gas particles memorized or not? Because if you know KMT for gases, there's four things, right? If you know those four for ideal, and anytime they don't mention it, if they don't say the word real, they're talking about ideal, you basically, do you have it memorized or not? And then you can just go through and cross them all out. So just to review, gases move rapid, random, and straight. They have no volume. When they collide, they transfer energy with no loss, and they have no attraction. That's a quick summary. And if you notice, for the ideal gases, it's a lot of no's. All right, so gas particles strongly attract. No, they have no attraction. The volume of the gas prevents random motion. No, they move rapid, random, and straight. D, gas particles travel in curved paths. No, rapid, random, straight. C is your answer because it's the only one that's true. Energy may be transferred between colliding particles. Now, if you notice, they didn't mention the with or without loss part. That's fine. For these types of questions, C is the most correct answer. It's the only one. If they would have said with loss, then I would say that C would be incorrect and there'd be no right answer, but C is the most correct. Number three, one reason that a real gas, so now notice they specify real, so now we're going to do the opposite of ideal, deviates from an ideal gas, is that molecules of a real gas have what? Straight line motion? No. Negligible, that means no volume. Nope. Forces of attraction? Yes. And then no net loss of energy on collision. That means that they transfer energy without loss. That is clearly A, B, and D are all for ideal gases. C is the only one that's opposite. 4, as the temperature of a sample of gas increases at constant pressure, so notice, temperature's going up, pressure's constant, so I ignore it. What does the volume do? So if you remember on your notes, there's a specific part that talks about the relationship between temperature and volume. So if you know that, and again, we will do this in a lab, you would know that if the temperature goes up, the volume has to go up because they are directly related. Number 5, as the space between molecules in a gas sample decreases, the tendency for the behavior of this gas to deviate from ideal. So let's break this question down. So as the space between molecules in a gas decreases, that's a fancy way of saying as the molecules get closer together, the tendency of this behavior to deviate from ideal, that is a fancy way of saying do the opposite of ideal, which they could have simply said become real. That's what deviate from ideal means. So as the molecules get closer together, the gas becomes more real, or the tendency for the gas to become more real does what? Well, it increases, because we mentioned that if you want to make a gas behave ideally, you need to separate the molecules with high T and low P. That's straight out of the notes. So therefore, if you make the molecules get closer together, you'll do the exact opposite of making them more ideal. You'll make them less ideal. You could say that they would deviate from being ideal, or you could say that they become more real. There's a number of ways to word it. And the last one, number 6. If the pressure on a given mass of gas in a closed system is decreased, so they want us to decrease the pressure, and the temperature remains constant, so that means ignore the temperature completely, what does the volume do? So I don't care about the mass. That's really just unnecessary. What they're really saying, if the pressure decreases, the volume will do what? And again, this is straight out of the notes, but part of the issue is reading through the question and trying to figure out what you need to really focus on and what you need to remove from the question that really isn't applicable. The mass part has nothing to do with it, and neither does the temperature remaining constant. I mean, it's important to know, but once you know that it doesn't change, you also now know to ignore it. And then in this case, if the pressure decreases, the volume would increase because they are indirectly related. And again, in your notes, and we are going to do a lab on that at some point.